turn on with audio. I did change my battery today, so it should be good for a week. Let's see, just making sure that we are maximizing the screen here. There we go. Okay. All right, so what we'll do first is to do a quick look at what we were talking about last Thursday. Actually, last Tuesday would be more correct, because last Thursday I think we were talking about the practice exam. So the actual exam is not this Thursday, it is next Tuesday. So we have 1 week until the next exam. So I'll be looking for something that is 1 week old, and today is the 12th, so it will be the 5th. There we go. All right. And I believe we have started to talk about the stack. I could be wrong. Is that right? Okay. So let's see where on the stack we are at. Let's see, this is... F says I have nothing to do. The difficult part, Oh, Tech, hold on a second here. How do we know that C has 35 in it? Find okay, there we go. Something to help illustrate that. All right. I don't have exact. So we are talking about the stack pointer. And I think we talked about, how we maintain the stack, how we store additional information on the stack, and how we get information, how we store and how we retrieve, from the stack. So let's go to that particular module first, because this part does have a module corresponding to it, and it is it's after the control structure. It is right here, calling and returning from subroutines. So I'm hoping that most of you, have read, this module, just so that you know the topic, before we get into this in class. Okay, so I'm going to zoom in a little bit. There we go. So what we're going to do is to continue the discussion. This is, I think, where we left off. Where we left off is how the stack pointer is initialized. It is initialized to point to 1 byte past the end of the entire stack. And that's okay. We're not going to access anything that is not a part of the stack, because in order to store something, the first thing we do is to decrement the stack pointer. So that will make the stack to point back to a portion of the stack, and as a result, it's going to be okay. So this is the push, which is also known as how we store data into the stack, and this is the pop, which is how we retrieve items from the stack. This is where we stopped last time. I am assuming that you guys have read up to this point, so we're going to continue on to section 4. So section 4 is translating these operations into assembly language operations, into assembly instructions. Okay. So are we ready to move on from here? Okay. So, well, actually, one thing we can do is to look at this and go, so we can do this in a slightly different way. What I'll do is I'm going to use mousepad. So instead of reading my own notes down below this section, I can do this side by side. Okay. And we can say, okay, this is C code. What do we do in assembly code? Okay, this is the push, and this is the pop. Okay. So popping and pushing are actual technical term, in stack operations. This is how we store. This is how we retrieve. And then there's the initialization. So the initialization is SP is stack, which is the name of the array, plus stack size, which is just a number that is indicating the number of locations on the stack. All right, so we'll do this one by one. Okay, in other words, what we'll do is we'll say, well, how do we decrement the stack pointer? But to answer that question, we have to understand, where's the stack pointer? Okay, in the architecture. So if you open up the architecture, you will find that there's no register designated as SP. Now we have PC, the program counter, We have the instruction register, which is not accessible in any way in software. We have the registers in the register bank, okay, registers A, B, C, and D, and those are certainly accessible from your instructions, okay? But we don't have a stack pointer. So what we'll do is we look at those 4 registers and pick one and say, you're it. You are the stack pointer now. Okay, and that's it. That's basically as arbitrary as it is to find one register and say, you are now the stack pointer. Okay, so we'll go ahead and start up LogicSim. Okay, so that we can take a look at the processor. And we'll go ahead and resize that too. There we go, a little bit that way. There we go. Okay, so we're going to look into the register bank and say, out of these 4, which one is going to be our stack pointer? So by convention in this class, we use register D as our stack pointer. Is that okay? Now, that means, we are only, so register D is not quote unquote born special, okay? It is born as equal and as, basically the same as the other 3 registers. It is just by convention that I choose to use register D as my stack pointer. Is that okay? Yep.
Are you just choosing D because it's the last register? If you had
more
registers, you would just choose like M.
Yep.
That's awesome. Gotcha.
Yep. That is somewhat the convention in industry as well. So if you look into some architectures, this is what we call general purpose registers. In other words, if you look at the computer architecture itself, all registers are the same. Okay, you can add with any 2 registers, you can load with any 2 registers, you can store with any 2 registers. So all of these registers are capable of doing exactly the same thing. So there's nothing special about the architecture or the ROM at this point about register D. And this is called what we call a general purpose register architecture, as opposed to a special purpose register architecture. So in earlier architectures, such as the x86 architecture and the ones before that, there are certain instructions that will only make use of a particular register or 2 particular registers. But those 2 registers are, so certain instructions are special. They would only use certain registers. With this type of architecture, all instructions apply to all registers equally. So there's nothing special about register D. Is that okay? All right. So we'll go ahead and take a look at the instructions. What if we use register D as if it is our stack pointer? So how do we decrement a register? So let me just make it clear, okay? Assume register D is the stack pointer, okay? So how do we implement that, decrement? I think I just told you the answer. Decrement, yep, decrement D, that's it. That's all we do. So assuming register X is the register that is providing the data that we want to store in a stack, how would you write that as one single instruction? Yep, st in parentheses D, and then we use X. So X can be any one of the registers, including D itself. There's nothing wrong with storing the stack pointer itself onto the stack. Now, why you want to do that is a whole different question. Okay, it can be done. It's just that why would you want to do it? So are we okay so far with this? All right. Okay. So next we look into these 2 instructions. And the question is, how do we reverse this, right? This is the reverse of the store instruction. So which instruction should we use? Load, very good. So load, and this time, X is the destination, and then in parentheses D. So the way I use the syntax in the assembler, or the mnemonic, is the parentheses around the register, basically it's a visual cue to say that it is dereferenced. Okay, but it is no more than just a construct, okay, in syntax to emphasize that we are dereferencing that particular register. Is that okay? So it's not because of the parentheses that we are dereferencing. the parentheses are basically declarations to basically say, yep, whatever is inside the parentheses in this case is being dereferenced. It's a major change or shift of mindset because C and C++ are syntax driven. Okay, when you apply the asterisk, it means we are dereferencing something. Assembly language, on the other hand, the mnemonic, is quite the opposite. Okay, everything that we do with a mnemonic is basically declaration to say that, okay, we can express this opcode this way to make it easier for people to deal with. So it's really kind of the opposite of how things are syntax driven in C and C++. Okay, what about this one here? We're incrementing the stack pointer. How do we do that? Yep, increment D, that's it. So now we got the push and the pop. So now we have to decide where are we allocating the stack. Now this part is interesting because there are several ways to do this. You can certainly allocate, okay, a portion of the stack and say, okay, this is a part of the stack, but we don't have to do it that way, okay? Because the way we use RAM is your instructions start with location 0 and it grows to higher locations. So that means if you don't want your stack to grow down and overlap with your instructions, it probably is a good idea to start at the very end of the entire RAM and say the stack starts there. So you have instructions going from low locations to high locations, and then you have the stack starting at high location going toward low location. And hopefully your stack does not step into the instructions, because when that happens, your program gets corrupted. Is that okay? So what is the highest address of this particular RAM module? You can say in base 10, base 16, or base 2. We have an 8-bit address port, right? So with an 8-bit address port, what is the last location? 255, okay? Because 256 requires 9 bits to represent, okay? So you might say, oh, so we want to initialize the stack pointer to 255. But that would not be correct because 255 is the actual last location. We want it to be 1 byte past the last location. So the way we're going to initialize the stack pointer is this. You go like, what? This is the first location. Well, that's because when you add 1 to 255 and you only have 8 bits, it becomes 0. So the register D, or the stack pointer, is actually initialized to 0. Then you might say, but then the first push operation is going to clobber the first opcode of the instruction. Nope, that's not going to happen, right? Why is that not going to happen? When we try to store the first byte onto the stack after the stack pointer is initialized, why do we not have to worry about the first byte of the instructions at location 0 being clobbered?
We decrement the stack pointer?
Yep, we decrement the stack pointer first. So that means the stack pointer is pointing to -1? No, because it's pointing to 255. Okay, you subtract 1 from 0, you can look at that 1111, 1111 as -1, but when you apply 1111, 1111 to the address port of RAM, all it does is to say, oh, I see you're interested in the last location of RAM. That's basically the interpretation. Okay, so everything is up to the interpretation. When you apply that bit pattern to the address port, what does it do? Okay, it just goes to the highest possible location because our RAM module only has 8 bits to specify the address. Is that okay? So are we okay with all of this stuff here? Okay, so we got push, which is to store something. We got pop, which is to retrieve something. This is how we initialize the stack pointer. But what about the content of the stack itself? Do we have to initialize that? The answer is nope, we don't. Okay, we just overwrite a location when we need to. Is that okay? Are we okay with all of this discussion up to this point? Okay. So what we'll do next is we are going to go back to the notes, okay? Because I just want to go back to the notes so that you guys know where we are at, okay? This is how we call a subroutine, and the second part is how we return from a subroutine, okay? So instead of just staring at the code here, let's go ahead and write a C code, write a little bit of C code, and then we'll try to translate that C code into assembly code. So very typical, we have main, okay? So everything in a C program starts with the main program. And we'll go ahead and say main call is going to call f, and it's going to return 0. And the f is a subroutine that does not do a single thing. And it returns void, so that we don't have to specify the return value. So the question is, given this is the code in C that we want to translate, which doesn't do a single thing other than illustrating how to call and return from a subroutine, how are we going to do this? Okay, so this part is completely, not going to be there in assembly code, and this part is also not going to be there in assembly code. This is not going to be there in assembly code. This one, we're going to just say halt, okay? Because there's nothing to return to when it comes to the toy processor, because you are not writing code with the assumption that there is an operating system to help you clean up when the program exits. When your program is done, you just get into the halt instruction, and the program just gets stuck with the halt instruction, okay? But we have talked about this already. So the real important point here is, but how do we call f? What do we need to do in order to implement a simple call to a subroutine in C and C++? We kind of know that at some point we have to do this, right? It kind of makes sense, okay? It kind of makes sense that at some point we want to jump to f, which is the label corresponding to the function f, okay? But if we just do this at the end of the invocation of f, we wouldn't know where to go back to, okay? So it might make sense also to use a label here, and I'm going to use a really long label name for now, just because. Is it okay for me to erase this part here because we are done talking about this? Yep. Okay. So we'll go ahead and erase that. All right. So it might be a good idea to label this point here and say, I'm thinking about something that's really long, but that may not be the best way. But we'll say return point after call, okay? Yes, it is kind of long. Is that okay? So we say jump to f, then we'll go ahead and go here. So the only way you can implement a C subroutine in assembly is to turn the name of the function into a label, because that label designates where we are going. There are no curly braces in assembly code. We can forget about that. So the only thing f is going to do is to return to the caller, which is in main, right? So at this point, it might seem that, hey, that's pretty easy. All we have to do, now don't copy this, all we have to do is to say, let's jump back to return point. Oh, yeah, my screen is getting that too. Don't know exactly why. Return point after call. Okay, that seems to get the job done, right? We transfer control to the subroutine f, and then since the subroutine doesn't have anything to do, it would do the return immediately, which is another jump back to the label that is after the JMPI, which is appropriate, right? Because the next thing we want to do is simply the halt, and we're all done. Seems to make sense. But this idea doesn't work. Why doesn't it work? There are many reasons why it doesn't work, but the quickest way to explain this is, what if in the C code we have a second call to f? Then we have a problem, okay? Because getting from the caller to f is not a problem, okay? We can always just do a JMP IF, and we end up in f, okay? Not a problem. The problem is, how are we getting back from f to where we are supposed to go back to. Is that okay? You can see how this is going to be a problem because the second time we call f, it's going to use the same JMPI to return point after call, which means now we have an infinite loop. And that's a problem. Yep.
Can you number them?
Hmm?
Can you number your returns?
It won't help. It's not going to help because how can the subroutine being called understand where it is supposed to go back to? Right?
Like an incrementing label.
Labels are concepts that only exist during assemble time. So that means those concepts they basically disappear when you have your object code or when you load your program into RAM. So, well, maybe we should use the stack, right? That little tool that we talked about earlier that can store and retrieve things. Maybe we should use that. So the way we're going to do that is we have another return point here. Okay, we say return point one, okay, after call, and we'll call this return point two after call. Okay, so now we have two distinct labels, which helps, right? Because now we have 2 points to return to, and they are now distinct. But we don't want function f to have to know those names, okay? So this is not gonna work, okay? So the question now is, how do we get that, basically get it stored in a way that the subroutine knows how to retrieve? Yep.
Would you have to push it to the stack before the jump?
Yep, that's exactly.
Instead of telling it what label to do,
Mhm.
just have it pop whatever was on the stack before.
Yep, exactly. So very good. So this is what I'm trying to lead you guys to think, is to say, okay, we talked about the stack, okay, and then we suddenly talk about something that doesn't seem to have anything to do with the stack. What is the connection? Well, we need a way to remember, where we're supposed to go back to. The stack is a global structure, which means everybody has access to the stack, the subroutine, the caller, and so on. Okay, so that means the caller, which we quote unquote call main, is going to store the return point one, before the JMPIF, the first one, and then the subroutine just has to go to the stack to retrieve that location, and then use that to say, oh, I need to go back because I stored this information earlier. Yes?
So, do we actually need the labels then? Is that what
Yes, we do. Okay, that's a very good question. At this point, we are going to use labels. At a later point, we can use something that's a little bit tricky so that we don't need labels anymore. Okay, but at this point, labels are easier to understand, and we'll do it with labels first. Okay, so that's a very good question. Okay, so what we need to do is to somehow store return point one after call onto the stack. Okay, so what we want to accomplish is to push return point one after call, and it would seem to make sense for the second call to have something like that too, except we'll be pushing the other label, right? Return point two after call. Okay, so what we do is now we try to remember, right, from before, how are we going to do this? Well, we can decrement the stack pointer and then do st, right? Okay, seems to make sense, right? Store the label to where D is pointing to, except the assembler is going to barf. The assembler says, nope, cannot do this. Why not? When you look up the st instruction, okay, so let's do this. Okay, I'll do this one time because I think it's very important for all of us to understand why this is not going to work. So we'll go to the share drive. Okay, so let's go to the share folder. And then we go to the processor subfolder. Okay. The first thing we do is we look up opcode. Okay, the opcode table. And then we look up the st instruction. The st instruction is last one right here, okay? So when you look at the ST instruction and you look at column B or column C, it says, column C doesn't tell you much. All it says is, star y equals x, which means, hey, we should be able to do it because x is just a label. But when you look up the top of this list here, it says x has to be a register, y has to be a register. Okay? Return point 1 after call is not a register. We have only 4 registers, and they are A, B, C, or D. Yep.
Did you say the label is like a bit accurate? It's not really what's in the register, but it's like the location.
It is,
Label?
a label is no more than just a number.
Yeah, just
Yeah, it is just a number. So it doesn't work with this scheme because apparently if you use x, if you try to specify a label for x, it only has 2 bits to represent it, and 2 bits is not enough to represent an address. Is that okay? Besides, okay, so when you look this up and go like, so does that mean we can store a 0 to where a register point to? Because hey, that works, right? Because 0 can be specified by 0, 0. The question is, what is that 0, 0 representing? Register A, exactly. So we are not storing the constant 0, 0 into where y is pointing to. We're going to register A and say, hey, register A, your content is now going to be stored at the location of y. Register y, whatever that is pointing to. How do we know that? This table doesn't tell you anything like that, right? So how do we know that this XX is not specifying the constant that we are storing, but instead it is an index into the register bank to specify a register to store into RAM? How do we know that? That has to do with, okay, that has to do with something that some of us do not want to think about, but if you want to pass this class, you have to think about. It has to do with the ROM of the processor. You go like, what does that have to do with the ROM of the processor? Well, let's think about STDA, okay? So XX is 0, 0, and then YY is 1, 1, okay? So that will give you an actual opcode of what? Come on, you guys know that. Okay, it starts with F because store starts with 1, 1, 1, 1. Okay, the most significant 4 bits are 1, 1, 1, 1. The least significant 4 bits is XX and YY. XX is 0, 0, right? YY is 1, 1. So we have 0, 0, 1, 1, which is F3. Very good. So now we say, okay, so what does F3 have to do with what an instruction can and cannot do, or how it gets the job done? This is another trick that you can do to try to understand how the instructions work, which is one more time, okay, I know I'm sounding like a broken record, but I heard this is actually good parenting technique, so I'm going to try that on you guys. So we'll go ahead and try this technique, okay? We'll type in F30 here. Okay, I'm injecting, okay, I'm not even bothering with the RAM. I'm injecting the content of F30 to go straight to the location F30. What is significant about the location F30 in the context of what we are talking about? This is the microcode corresponding to the opcode, okay? Hold on a second here. There's too much code that we're talking about. What is opcode? Where does opcode live when you write a program? In RAM. And what about microcode? Where does a piece of microcode live? In the ROM. What is their relationship? One is something that you can specify as a programmer. That would be the content in RAM. One is hard-coded into the processor, which is the content of ROM, okay? So the microcode in ROM is what implements an opcode. In other words, this particular bit pattern that we see here, 1503882 in hexadecimal, specifies a whole bunch of bits, 26 bits to be exact, that specifies all the pathways and also what components should be enabled, what components should be disabled and are not enabled, in order to control what happens with the processor. Yes?
So it's like RAM is the middle person between us and the process. So we tell the RAM what to do, and the RAM tells the ROM what to do.
Yes. So RAM is kind of what a coach will call out in a football, as a play, right? We use that analogy, okay? And the ROM is the playbook, okay? You have a whole bunch of football players who did not memorize all the plays. So what are they going to do during a football game when the coach says, "Oh, I want to play 2-5-1," okay? So the entire team will have to now, huddle, right? Because there's only one copy of the playbook. They open the playbook and go like, "Okay, coach call for play 2-5-1. What are we gonna do?" Okay, quarterback, you're supposed to be here and try to do this. Receiving end, receiver. How is that called? The person called wide receiver. So wide receiver, you're supposed to go to the left and go straight to the back of the other side. Running back, you're supposed to be here, relative to the quarterback, and then linebackers, just do whatever you can to block and make sure the quarterback is safe. Okay, so now they look at it and go like, okay, so each player now knows what to do. That's what this playbook is doing. Okay, RAM is basically what the coach is calling. It's like, okay, we need play 2-5-1. Who are the players? All the registers. Those are the players. Okay, each one has a specific role to do. Okay, at certain times, a particular register may not have anything to do with that operation. It's disabled. Okay, but other times they might have something to do. Are we doing okay so far with this analogy? Okay, especially with, if you don't understand football, we can use another analogy. I don't think there's a soccer analogy because soccer is a little bit too fluid to have to be something like this. But anyway, when you do look at all the bits, spewing out of the data port of ROM, this is how the store instruction gets done. Okay. Now, specifically, which two bits are the 0, that we just talked about? Okay. Where are those two zeros? Those two zeros are, let's see, it's bit 0, 1, 2, 3 is this first 0. Bits, 0, 1, 2, 3, 4, 5 would be the 3, and then 5, 6. No, I miscounted. Okay, 0, 1, 2, 3, that's this one. 6 and 7, so bit 0, 1, 2, 3, 4, 5, and then 6, 7. So bits 6 and 7 of the F30 are the two zeros that we talked about, the XX. Is that okay? So those bit 6 and bit 7 becomes bit 6 and 7 of the address in ROM. Does that make sense? No? Okay. So let's actually do the translation here. Okay. So this is, we're translating F30, okay? And we want to find out where the XX is located, right? So we can start with F3 first, okay? Why is the opcode F3 when we want to specify store DA? That's because we have 1111 as the fixed bits. We have XXYY as the bits to specify the registers. XX in this case is register A, which is 00. YY is register D, which is 11. And that's why we have F3. This is F, and this is 3. Is that okay? So when you look at F30, which is 1111, 0011, 0000, so the way we do the counting is this is bit 0, 1, 2, 3, 4, 5, bit 6 and 7. Is that okay? That is where you put the XX, okay? And you can see that XX, when you go back to the ROM, okay, when you go back to the ROM, that XX is only a part of the address of the content in ROM that we are using. In other words, that XX does not directly specify the value that we want to store. It only is used to get us to a place where this place, this particular bit pattern, 1503882, is going to specify what goes into ROM. What is stored in RAM. Okay, I'm just going to fast track a little bit here because I think we have done this enough times that you guys should be able to do it quickly. So what we need to do now is to look up the data port of RAM and say, who's driving this bus? Okay, who's driving this wire? There are not too many people can drive this wire. In fact, there's only one component that can drive this wire, which is this demultiplexer here. It is enabled, and the selection is 10, which is the correct one because we're looking at this output. So you can see how it is. We're connecting output 0 of the register bank to the data port. So whatever we are spewing out of output 0 of the RAM of the register bank is what we are using to update RAM at that location. Is that okay? All right. So now the only other question to ask is, what is output 0? Because we got 4 registers inside the register bank. So we use register output 0 select to find out. It's register 00, which is what we know as register A. This is Y, which means you have to combine the opcode table and also the ROM of the processor, and also look at what that ROM is enabling and how it is connecting components to understand how a particular instruction works. So are we okay with all the pieces? So you start with the mnemonic that you can type in fairly easily. You go to the assembler. The assembler just turns the mnemonic into an actual opcode. Then you use the opcode to look up the ROM. And then once you look at the ROM, that slice of ROM is what is directing the individual components of the processor to make that connection. This is what you need to understand to do well in exam 2. Is that okay? All right. And it's open book and open notes. You can bring this diagram with you. So, and I think once you know how to read this diagram, it's going to be very helpful. Okay. All right. So now getting back to where we left off here, I'm just going to erase this part. So I am hoping that we understand why this instruction is not going to work. The assembler will reject it. Okay. But even if you say, well, but register A is really just 0, the assembler will reject that too. Okay, because we need to specify some kind of register here. Then you go like, but that's not going to work because register A is uninitialized. Well, that's okay. We can always just go ahead and initialize it, right? So we can initialize register A as return point 1 after call. Then we're all good. Are we good? Are we doing okay so far with this? These 3 instructions, decrement D, LDIA, blah, blah, and then ST, this is how we push the return address on the stack. There's not a whole lot of need to copy what I have on the projector, okay? Because it is all, huh?
Are you recording?
I am recording because it's all here. So this is really kind of telling me who has been reading ahead of time and who has not. Who has not, but yet still care about this to write it down, I should say. Okay. So this is how we push the return address on the stack. Yes?
There's something to be said for writing things down with your hand in the conversation.
Yep.
So
even if you have read it already, but the important part is to not write down what is on the projector, but to write down what is in your mind right now, because that is not something that is being recorded, nor is it on the screen, nor is it in the notes. So, what is going through in your mind that is not something that is on the screen is what you need to really write down. Now it might help to print the notes ahead of time. Okay, and, it's perfectly okay. And then you can then jot down some notes on a post-it, stick it next to the topic, and that will basically give you the notes will give you the context, and then your post-it will supplement what is already written with your own words. So it might be helpful to do that too, is to kind of jot down notes and say, write something that is in your own words. But yes, having to go through that physical motion to write down something does help. There's some studies that shows that.
It's like one of the three things of retaining information. If you read it, you hear it, you retain it better.
But not when you're too busy writing and totally bypass what I'm actually talking about. Yep. So that is one thing that I want to make sure is you guys are not so busy writing down stuff that you're not listening to what I'm saying, or having the chance to ask questions when you say, hold on a second here, I don't really quite understand that. All right. So now we have a way to push the return address on the stack. This has to be there, okay, in order to continue execution in function f. So now the question is, what am I going to do here to retrieve the return address? Well, we talked about popping, right? So it doesn't seem too hard to do it. So what we need to do is to do a LD first, okay? So we do a LD into a particular register. Register A is okay at this point, okay? At a later point, we'll find out that register A has a special role, but only sometimes, okay? But in this case, it's okay. So we can use register A, and then we can now increment D to basically deallocate that byte that was used to store the return address, because we have just retrieved it. I don't need that location on the stack anymore, okay? But now we go like, what am I going to do here? Because the place that I need to go back to is not a label anymore, okay? Instead, it is something that is stored in a register, in register A. So how do I continue execution at a point where a register is telling me where I'm supposed to go back to? Okay, so based on the syntax of the mnemonics, okay, most people would say maybe something like this. It's kind of indirect like that, right? But instead of doing this, we can now go to the opcode table again, and this time we're looking through this stuff and go like, okay, is there any instruction here that might do what we need to do? Okay, so we'll go through some of these instructions. And let's see, it's not on this page, but we're getting close. There we go. We see it. Which one do you think will help? You might want to look at column C. Column C is the one that will give you the biggest clue of which instruction is useful, okay? So it sounds like we want to do something about the program counter, right? The PC. Because in order to control where you're going to execute next, you have to change the program counter. Otherwise, the program counter just keeps incrementing, right? It will just keep going in a linear way. So in order to break that linear execution pattern, the program counter needs to be updated explicitly. So that means if you look at column C, anything that has PC on the left-hand side of an assignment is candidate. Okay, but the current situation that we are in doesn't say it's conditional, okay? So anything that looks at a flag like this, okay, doesn't seem to apply. Flag, 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 definitely not apply. This one, PC is not used on the left-hand side. We can ignore that. This one has PC on the left-hand side, and it is not conditional. Then you go like, maybe we want this one. Then you look further, and you say, what is X? X is one of the 4 registers, right? So we are copying the register into the program counter directly. It's just like whatever this register has, the program counter is now updated to that value. That seems to be exactly what we want to do, because we already have the return address in which register? Register D is the stack pointer. We have it retrieved in register A at this point. So that means what is left to do is to say copy register A into the program counter, which is exactly what JMP A is going to do. Now you can see that there's no I in this JMP because it is not immediate anymore. Immediate means you have to supply a constant within the mnemonic to specify where you're going. But in this case, we're using a register. The value of the register is what is telling me where to go back to. Is that okay? So we now go back to here, and then we say JMP A is what we want. Are we doing okay so far? Yep.
So we can do all that without any immediate like JZI. You can just use JZs by storing some values.
Yes, you can, but it is very cumbersome to do the non-immediate version of the conditional branches because you have to first initialize a register to tell you where you need to go. So the LDI are not 100% necessary because you can certainly do it with the non-I version, but to use the non-I version, your program gets insanely long and tedious. So this is a trade-off between cisc versus RISC. Remember complex instruction set computer versus reduced instruction set computer. So the toy processor is not a pure RISC architecture because we do have certain instructions that could have been done using other instructions, but for convenience and also in this case to make the programs concise enough that we can actually store in 256 bytes, we need the immediate version of those branches. But you're absolutely correct that the JXI instructions can all be replaced by the JX instructions. You just need to use one register to specify where we're going. All right. So getting back to here, we are done with the subroutine. This is all the subroutine needs to do is to retrieve the return address and then go to that place. So when we get to that place, okay, after the first call is going to go back to return point 1 after call, which means we're continuing execution at this point, which means we're ready to call F the second time. So if you want to call F the second time, you can just copy and paste this portion here, but you have to remember to change the label to return point 2. Because if you don't, it will return back to return point 1, which means now we have an infinite loop again. Is that okay? Are we doing okay so far with this? Excellent. Cool. So every time you do a copy and paste, it's not so bad. But if you have to do a copy, paste, and modify, it is not so good. Because if you forget about the modify or modify incorrectly, then the code is going to be wrong. So the question now is, well, is there a better way not to use a label? Because that seems really cumbersome. So the answer is yes. Okay, there's a particular notation in the assembler, and it's a fairly recent feature. Okay, is we can basically not to use this. Okay, but I'm going to keep the label definition for the time being. There's a notation here that says, okay, I'm going to comment this out. A dot has a meaning in the postfix expression. A dot means where we are now, okay? So a dot is representing the beginning address of the instruction that we're specifying on that line. Okay, so I'll say it one more time. In the postfix notation, you can use a dot to represent the address of the instruction that that it is a part of. So in this case, the dot is the address of the first byte of this particular LDI instruction. Now, why is that important? Because you can now calculate, you can use a postfix notation to calculate where you're supposed to be at after the call. Okay, so let's count. Where are you supposed to be at? Right here. Is that okay? This is the instruction right after the JMPI instruction. So this is where you want to return to. Is that okay? I mean, after all, return point 1 after call is the address of the decrement instruction. Is that okay? All right. So we want to know not the absolute address of the decrement D instruction. We want to know how many bytes are between the LDI instruction and the decrement instruction. That is what we want to calculate. But that can be calculated by counting, because the LDI instruction has 2 bytes, right? 0, 1, okay? ST has 1 byte, 3. JMPI has 2 bytes, 4, 5. Is that okay? So that means the decrement D instruction is 5 bytes away from the LDI instruction. Are we okay with that? Yes.
What is the store at 1 byte?
The store only has 1 byte because it's not an immediate instruction. All the immediate instructions have 2 bytes, and all the non-immediate instructions only has 1 byte. Okay, so let's count again. 0, 1, 2, 3, 4. Oops, I miscounted. 0, 1, 2, 3, 4. So I only counted 4 bytes. So we want this to be 4 bytes away. I need to double check that. Label does not use up any bytes. So it's 4 plus, okay? So that is the same thing, okay, as return point 1 after call. Should be the same. Are we doing okay so far with this? Okay. So let me just do it, just count one more time. This is 0, 1, 2, 3, 4. Oh, that means this is 5, okay. Because 4 is the second byte of the JMPI instruction, so the offset is actually 5. So let me count it one more time. 0, 1, 2, 3, 4, 5. Are we good so far? Yes? So if you use this approach, then the second one can be exactly the same as the first one, which means now copy and paste is going to work without needing to modify. Are we okay?
So that'll put you at the halt instruction.
That will put me at the halt instruction, which is exactly what should happen, because after the second call to F, we have return 0 in the C code. So that means in the assembly code, we want to end up at the halt instruction.
Can you explain what you mean by immediate and non-immediate?
Any instruction that has an I as the last character is specifying an immediate value as one of the operands. It can be the only operand, can be the second one, but it has one operand that is an immediate, which is basically just a number that you can specify. But that number has to be computable at assemble time, so it's not a runtime thing. You cannot change that at runtime. So LDI has the second operand being just some kind of expression to give you a value to store into the register. So it has an immediate, it takes up 2 bytes. JMPI is the same way. JMPI has a label or an expression in general that specifies where you're supposed to go to. Is that okay? So that means this technique can also be used with JMPI if you can hand calculate the offset between the JMPI location and where you want to go. You can do a dot, whatever number plus, and that can be used to specify where you want to go to. In general, that is not, something you want to do, but in the case of, pushing the return address, it is almost always 5 bytes away from the LDI instruction if you use this particular pattern. So it works. Yep.
When we're counting, is it just 2 bytes for the immediates and 1 byte for the non-immediates?
Yes.
That's it?
Yep. All right. So now we have something that might work. Yep, go ahead.
Sorry, did you say we could also build control structures with LDI then, or?
If you use the non-I version of the conditional branches, then you have to use LDI to specify where you're going. Yep. Which is very cumbersome. You can do it, but your program gets super, super long because of that. And it's not, so it's much more practical to use the immediate version of the conditional branches. Are we still doing okay so far? Yep, go ahead.
So in the function you're jumping register A. How does it know to jump 5? How does it know where to jump back to?
Okay, let's give these line numbers so you can direct me to the line number that you're talking about. Go ahead.
So in the function you're jumping back to register A.
But that A is retrieved from the stack. I don't really have to use register A. I could use register B or register C to emphasize the point that this register doesn't have to be register A. It doesn't have to be the same register that I use for pushing.
No, I understand that, but where does it know where to jump back to?
Because that was saved on the stack. Because the return address is pushed on the stack by these 3 instructions or by these 3 instructions. The stack is equally accessible in the subroutine, so we are just immediately retrieving that from the stack. Now, these are all very good questions, so I will try to answer some of these questions using the trace analyzer. Okay, the trace analyzer is very, very good with this type of program. Okay, so what we'll do is we're going to finish this program first because we have 2 more things to do, especially if we are to use the trace analyzer. If you plan to use the trace analyzer, the first opcode has to be no op. Okay, it's just a bug in LogicSim that requires that. The second one that is sort of missing, but it's not really necessary, is the initialization of the stack pointer. If you're running this from in the context of a trace analyzer, which means you're running on the command line, you don't need to initialize a register because all registers they all start with a value of 0. Okay, but in case you're not 100% sure about that, you can always do a LDI register D with a 0 to initialize the stack pointer. But this takes 2 bytes, right? Because it's an LDI instruction. If you're super frugal about how many bytes you use in your program, this can be done with 1 byte when we say subtract D from D. Does that make sense? If you subtract the register from itself, it's guaranteed to be 0 after that. Okay. Now you might say, but then we don't need LDI D0 anymore. No, we still need something like that occasionally, because LDI D0 does not go through the ALU, which means none of the flags is going to be changed. Is that okay? So LDI does not affect the flags. But on the other hand, subtract DD does affect the flags. Now we know exactly how it is affecting the flags. Okay, let's go for the 5 flags again. The carry flag is going to be cleared because you don't need to borrow, subtracting 0 from 0. I mean, subtracting a value from itself. See Z, okay, the Z flag is guaranteed to be a 1 because after the subtraction, the result is guaranteed a 0. CZS, okay, sign is also guaranteed to be 0 because the sign flag of 0 itself is 0. Overflow is going to guarantee to be 0 as well because a value being subtracted from itself should not overflow. Okay, and then the last one is L. Okay, L is also guaranteed to be 0 because a value cannot be less than itself, signed or otherwise, right? So we know that only the Z flag will be set after the subtract instruction. But if you need to preserve the flags, then you can use LDI so that those flags are preserved. In this case, we don't care about the flags because there are no conditional branches right after it. So we can just, hey, we'll just go ahead and use subdd to initialize the stack pointer. Okay, so that completes the whole program. We'll go ahead and copy and paste this into the assembler, and then we'll go ahead and run it. Yep.
So you're using dot instead of return point after call. So we would have to eliminate using labels.
We can eliminate some labels, but not all. So when you have conditional branches, it would still be better to use labels. But when you're specifying a return address, that is a more convenient way to specify a return address. So we go into the assembler and we go to source. paste. And wait until, oh, we did get rid of this stuff here. It doesn't really hurt, but it's just extra stuff that we don't need. All right, so the program is assembled. Oh, okay. Nope, okay, it's all good. So the first thing we want to do is to go to the Assemble tab, because we want to check out a few things, okay? Particularly, we want to check out whether the way we use the .5+ is going to give us the same address as the label itself. You can see it quite clearly now, right? I mean, you can see the return point 1 after call is 8. This is decimal 8, okay? But when you look at the actual immediate value that we specify with the LDI instruction, it's 0.8 in hexadecimal. 0.8 in hexadecimal is the same as 8 in decimal. So we know that calculation does work out, okay? You can also look at the second LDI instruction. So with the second LDI instruction, which is here, we can see that the immediate constant is 0e. That's from calculation. That's from the 1.5+. But when you look at the label, which is return point to after call, it is 14 in decimal. 14 in decimal is 0e in hexadecimal. So we know we can double check and confirm that calculation actually does work. Are we good so far? Okay, because it's always good to double check, okay, especially if it is the first time you do something that is slightly different from before. It's always good to double check and make sure that works. All right, so after illustrating this, we can now go to the RAM file tab, download the program. Okay. And we'll call this callret callreturn.csv. Go to Logisim, Control R, because I did inject something into the microcode pointer. So now we go here, we load the image, okay. /temp/callreturn.csv. Okay, so this is not going to show a whole lot. I mean, if you do a Control T the whole time, you would actually see, how the stack is being used and how the values are being retrieved, how the stack pointer changes and all that stuff. But it's really kind of tedious to do this. So instead of doing that, I'm just going to turn on, the ticks and then stop it again. And we can see how the program counter is now stuck at 0f. Which is the 1 byte after the halt instruction. Okay, how do we know that? We go back to assemble, and we see the halt instruction is at location 0e, and 0f is 1 byte past it. And that's normal, because remember, when we have a rising edge, when the microcode pointer is at location 001, it auto increments the program counter. So it is okay for the program counter to be 1 byte past the opcode that we are stuck at. Are we good so far? Okay. So instead of using the simulator, okay, we'll close it. We'll go ahead and do this on the command line so that we can use the trace analyzer, which is the best way, I think, to do this. So this is going to be a little bit long as a command line, but it's okay. We'll copy this part. Okay, and then the first thing is to specify where the processor 0003 file is. So we'll go ahead and locate that. Okay, then we have to specify a whole bunch of stuff, right? So we have to specify -tty table to specify that this is not going to use the GUI. Okay, and then we have to specify the load to the RAM file that we're dealing with, and that's in the temp folder called return.csv, and then we have to redirect the output, because otherwise it'll just spew out stuff on the screen, which is not going to be very helpful. So we redirect stuff to, I just called it log.tsv. Now the program is all done. We switch back to the share folder, and then we reopen the trace analyzer spreadsheet. Okay, go to sheet 1, go to File, and then we specify import. And the file this file we do have to upload. Okay. And it's log.tsv. It's tab separated. And then we have to carefully select these options. Replace current sheet, tab separated, and do not convert anything into numbers. So we do the import. All right, so this is all done. And you can skip sheet 2, which is an intermediate spreadsheet to do some of the calculations that is needed, and you can skip all the way to analysis. Okay, so this is the analysis sheet, which has a lot of empty rows, because the empty rows are transitions that are not particularly important when it comes to the interpretation of the trace. Okay, so now it's all done. We can see that when the program counter is 0, 1, the Z flag got a value of 1. And why is that? Without even going back to the source code, can you guys remember why the Z flag gets a 1 because of the instruction at location 0, 1? Is it because we're subtracting D from D? Okay. All right, very good. So what you need to do is to keep an eye on how registers are getting changed. Column D will tell you when a register got changed. This is when we do the decrement D, so the register D is now FF, okay? And the next instruction has these side effects. It writes to RAM, okay? So there are 2 locations, let me see. Nope, those are RAM read. Okay, let me do this trick here. And you can do the same trick if you have already made a copy. You can drag this bar so that the heading of the columns they stay put, and you can scroll the rest. So that makes it easier to read what is going on. So this is RAM read. We are reading location 08 and location 05. And as a result, we change register A to 08. What are those things corresponding to? Which instruction are we dealing with here? Well, one register got changed, so it has to be it's an LD instruction, right? It's an LD-ish instruction. But the 08 is read from location 08, which means it is a LDI instruction. This is the LDI instruction that loads the return address into register A. Is that okay? Are we doing okay so far with this or not? Okay, now when you are doing this, it helps to open the assemble tab of the assembler alongside right next to the trace, because that way you can correspond the addresses of column A in the trace analyzer with the actual addresses of the instructions in the assemble tab. Okay, but I don't really have a whole lot of room in this case. Okay, we get to the next instruction, 05, okay, and this one does change RAM. Location FF of RAM is now overwritten with the content of 08. That's how we store the return address on quote-unquote the stack. Okay, is that okay? And then what do? Well, we get to location 06. Location 06 is our JMPI instruction. Okay, because of the JMPI instruction, you can see the next location that we execute is now at location 0F, which is the label F itself. Okay, the label corresponding to the function F is at location coincidentally 0F in memory. Are we good so far? So what does it do? The first thing it does is to retrieve the byte that we have stored on the stack into a register. In fact, it retrieves that and put it into register B, because we have a LDB comma in parentheses D instruction, in the subroutine being called. So we have just retrieved the return address. The next thing we do is to increment the stack pointer, because that location on the stack is no longer useful. And you can see how register D is now updated. It's updated from FF to 00. So it is an increment. Is that okay? And then after that, what do? we have a JMPB, right? So the JMPB instruction, which is at location 11 in hexadecimal in the program, doesn't change anything because the program counter is not being logged. Well, it is being logged, but it's not reflected in this particular sheet because we only track these names. But we can also see how from location 11 in RAM, the next location we execute is now at location 08. So whenever you see consecutive addresses that are not off by 1 or 2, we know a branch has happened, a jump has happened. Does that make sense? Now, sometimes if it is off by 2, it can still be a branch, but that's very unusual, okay? But it can happen. But if it's off by more than 2 bytes, it's definitely a jump, okay? So now we're jumping back to location 08, which is the beginning of the second call to F. Once again, we are decrementing the stack pointer to make room for the byte that we are about to store. And then we change register A to the label or the location of the return address. We change A to be the return address. And then we store the return address on the stack. And then we continue execution at the subroutine because once again, you can see 08 jumps all the way to 0. Oh, this is 0B. So this is still in the caller. And in this case, this is the branch instruction. This is the JMPI to call F the second time. Now we are in F, the subroutine. In the subroutine, the first thing we do is we retrieve the return address from the stack. Then we increment the stack pointer to indicate that location of RAM is no longer in use. And then we have the JMP instruction, JMPB, to go back to the to main. And this is in main again, but this is the halt instruction, and that concludes the execution of the program. So the trace analyzer gives you a summary of how things got changed during the execution of a program. So instead of having you to control T the whole time and then pan around to see what is changed, this gives you a summary of how things got changed, and you can review it. You can print it out, okay? You can review it, as many times as you want. You can copy and paste. I would not remove these empty rows, okay? Because if you remove the empty rows, the spreadsheet itself will be broken. But you can copy this to another spreadsheet. Then you can do whatever you want. You can collapse all the rows that are empty, print it out, and then have annotations on your own, on those cells. So that will help you understand what is going on when we are looking at a trace like this. Is that okay? Yep.
Do you recommend logging from Logism, or
It depends on the complexity of the program and also depends on what you want to do. When we're dealing with programs at this point, because I'm assuming that we are past the point of trying to understand how opcode gets the job done, okay? So once we are looking at things from the kind of more of a macro perspective instead of the micro perspective, the trace analyzer will help you visualize what's going on with the program a lot better compared to doing everything inside the GUI.
yeah, I had the question and it just fell apart.
But did I address the question? Okay. Yep. So I do recommend looking at things from the trace perspective. So if you have a trace that is particularly important, okay, and you don't want to have to copy the trace analyzer itself over and over again, what you can do is you can just copy the cells that are important to you and into a new spreadsheet. So in that case, you'll be copying just the content. You won't be able to do update all that stuff again, but you will be able to insert your own comment. Okay, to insert comment, it's just like right click and say insert. Okay, maybe not there, but you can do it from here. You can just insert your own comment and say, this is where the halt instruction is, and so on. Okay, I'm not going to do this because if I did that, it would affect the original trace analyzer, and that's not good because this location does not always correspond to the location of the halt. Excuse me, of the halt instruction. So are there any questions about this whole process? I know there's a lot of moving parts, okay? But if we're building all the parts on top of parts that we already understand, then it's okay. Because we're just stacking stuff on top. So I think for those people who took cisp310 from me last year, you're starting to see some resemblance between how we use columns in a spreadsheet in a trace and what we know as a stack in this case. And that was the intention. Any questions about calling and returning? In terms of concepts, it's actually a fairly simple concept, but you do need to understand the instructions, and how everything works, in order to get this part. So that's the part that makes it kind of complex. All right. So with that being said and done, let's go ahead and open another module. And that one is stack operations right here. And I'll give you guys a week to work on this. So today is the 12th, so 1 week would be the 19th. So November 19th at 9 a.m. Okay, there we go. So you can start to work on this today in the lab. But you can also use the lab time to kind of do the same kind of stuff that I did today, just so that you're familiar with the process of using the trace analyzer. So we doing okay with this? All right. So I do want to talk to two people specifically. So I'm going to write down the last name here. I think these are the last names. There we go. So just stay a little bit behind class and come to me, and I just need to talk to you a little bit. And then the rest you can go to the lab and I'll be there as soon as possible.